There is a wall in the city of Cusco, on a narrow street called Hatun Rumiyoc, where a single stone meets 12 neighbors along 12 different angles. The stone is roughly the size of a large refrigerator. The angles do not run straight. They turn, they bevel, they curve. And not one of those 12 joints, half a millennium after the wall was finished, will admit a razor blade, not the edge, not the spine. Tour guides bring blades. Tourists bring credit cards. Engineers bring feeler gauges. None of them go in. On the order of magnitude that ordinary engineering measures fits, perfect. The wall is older than the Spanish conquest. It is older than the printing press. It is older than the state of Florida. It was built without iron tools. The Inca had bronze and copper, but neither was used to shape the stones in question. It was built without mortar. It was built without anything we would today call a measuring instrument. No calipers, no levels, no rulers in the European sense. And it was built in a city that 2 centuries after it was finished sits at 3,400 meters of altitude, where building a wall takes longer than it does at sea level because human bodies move slower in thin air. For 4 centuries, European writers looked at these walls and concluded that the Inca had access to something we did not. Some claimed lost technology, since departed. Some claimed lost knowledge of a plant whose sap softened stone like wax. Some, more recently, claimed extraterrestrial assistance. All of these explanations have one thing in common. They are wrong. The Inca walls were built by men with stones in their hands. We know this because in 1982, a Swiss-American architecture professor walked into an old Inca quarry, picked up a stone hammer, and in 90 minutes fit 2 blocks together as tightly as anything in the Hatun Rumiyoc wall. This is an entry from the Codex about the most precise stonework ever produced by a civilization without metal tools. We are going to look at the technique, the quarries, the transport, the labor cost, and the question that nobody seems to ask, even though it is the only question that actually matters once you have the technique solved. The Codex is open. We start at the wall. To understand the scale of what we are looking at, you have to understand the geography. The Inca Empire, Tawantinsuyu, in their own language, meaning the 4 united regions, at its height in the early 1500s, ran along the spine of the Andes from northern Ecuador to central Chile, 2,400 kilometers top to bottom. Population estimated, depending on which historian you ask, between 10 and 16 million. Capital at Cusco, and across that span, distributed in dozens of cities, fortresses, and ceremonial complexes, was a single architectural language built out of vitted stone. The fortress on the hill above Cusco has stones that weigh up to 125 tons. Some estimates push individual blocks to 200 tons. 60 kilometers northwest in the Sacred Valley has a temple complex built out of red granite blocks, transported across a river and up a mountain. Machu Picchu, the famous citadel, is built largely from local granite, fitted in a tighter, more refined version of the same technique. Pisac, Chinchero, Tipon, Choqquequirao, Saraguro, Ingapirca, and every major Inca center across 2,000 kilometers of Andes carries some version of fitted stone walls. The empire built thousands of these structures. Most of them are still standing. 2 styles dominate: coursed masonry, rectangular blocks laid in horizontal rows like brickwork, but with stones precision-fitted instead of mortared, and polygonal masonry, irregular, multi-angled stones interlocked like a 3-dimensional jigsaw. Both styles are characteristic. Both achieve the no mortar, knife blade fit standard. The polygonal walls tend to be older, lower in elevation in the city, and reserved for the most important buildings. The coursed walls tend to be later, used for the upper sections of palaces and temples. Both are present in Cusco, sometimes on the same building, with polygonal foundations holding up coursed superstructure. The dating is important. The polygonal style at Sacsayhuaman is generally dated to the reign of the Inca Emperor Pachacuti in the mid-1400s, meaning these walls are roughly contemporary with the European Renaissance. Despite popular speculation, prehistoric. They are not from a lost civilization that predated the Inca, built by Inca labor under Inca command in the Inca period. The radiocarbon dates, the stratigraphy, the documented continuity of the construction crews, all of it places these walls firmly in the empire's own historical window. Now, with the geography and dating set, we can ask the question. And before we get to the right answer, we have to clear away 3 wrong ones, because the wrong answers have circulated so long they have become folklore. In increasing order of how seriously they are taken by general audiences, and how completely each one has been refuted by people who actually study these walls. The Inca had a plant whose sap softened stone. The story, in its most popular form, claims that an Inca craftsman would apply the juice of a particular Andean plant, sometimes identified as a small herb, sometimes as a root, to the surface of a stone. The stone would soften, like clay or wax, and the craftsman would press another stone into it, leaving a perfect impression. Then the sap would dry, the stone would reharden, and you would have a perfect joint with no labor beyond plant collection. The story has Spanish colonial origins. Garcilaso de la Vega, a chronicler of mixed Spanish and Inca descent writing in the early 1600s, mentioned the legend in his History of the Inca. He treated it as something he had heard. From there it traveled, picked up by later writers, picked up by tourists, picked up by mid-20th century mystery books. By the time it reached pop culture in the 1970s, it had become a confident statement. The Inca knew a plant we have lost. The problem is the chemistry. Stone, andesite, granite, limestone is composed of mineral grains held together by crystalline bonds. You would need to break those bonds at room temperature using a chemical agent. We know what that takes. Hydrofluoric acid attacks silicate bonds. Strong alkalis can do it given time. Various solvents can dissolve calcite, but none of these are present in plant sap in concentrations that would matter. Plants do not produce hydrofluoric acid. The metabolic cost is prohibitive, and the chemical itself is toxic to the plant. There is no candidate compound in any plant native to the Andes or anywhere else that would soften silicate stone. Materials scientists have looked. They have not found it. The myth fails on basic chemistry. Myth 2. Lost technology, some advanced civilization, Atlantean, Lemurian, antediluvian, take your pick, built the walls in a forgotten golden age, and the Inca merely inherited and reoccupied the ruins. The version that gets the most airtime claims the precision of the joints requires diamond-tipped saws or other implements that the historical Inca did not possess. There are 2 problems with this. The first is the dating. The walls have been dated by radiocarbon, by stratigraphy, by inscription, and by direct documentary evidence from Spanish chroniclers who watched the Inca build. We have eyewitness accounts of 15th century Inca crews quarrying and dressing stone. The chronicler Tieza de Leon, writing in 1548, described Inca masons at work and noted that they used hammerstones and abrasive techniques. The walls are not pre-Inca. The second problem is the tool marks. If you look closely at any Inca wall, and people have, with high-resolution photography and three-dimensional scanning, you do not see the smooth, glassy surfaces that lasers or diamond saws produce. You see thousands of small, irregular impact pits. These are the signatures of percussion tools, the signatures of stones hitting stones. The marks are not consistent with any modern tool. They are consistent in detail with what a handheld hammerstone does when it strikes andesite at a specific angle. Myth 3. Aliens. We do not need to refute this in detail because the previous two refutations cover most of it. There is no archaeological evidence for non-human builders. There is extensive evidence for human builders. Written records, tool marks, abandoned construction sites with half-finished blocks, quarry waste piles. The aliens hypothesis exists because the technique looks impossible to a viewer who has never tried to do it. We will see in the next section exactly how possible it is within 90 minutes. The man who solved it was named Jean-Pierre Protzen. Born in Switzerland, trained in architecture, eventually a professor at the University of California, Berkeley. In 1982, he traveled to Peru with a research grant and a question. The question was the question we have just been asking. How did they do it? And his approach was not theoretical. He went to the quarries. Protzen visited Rumiqolqa, the andesite quarry south of Cusco. He visited Kachiqhata, the granite quarry above Ollantaytambo. He measured tool marks. He photographed the abandoned blocks. And the Inca had left abandoned blocks at the quarry sites in the act of being worked when the empire fell to the Spanish in 1533. These half-finished blocks are the closest thing archaeology ever gets to caught-in-the-act evidence. They show what the Masons were doing. They show the sequence of operations. They show the tools. Protzen picked up the same kind of tool the Masons had used, a hammerstone, and he began experimenting. A hammerstone, in Inca masonry context, was a handheld cobble of harder rock, typically diorite or quartzite, weighing somewhere between 1 kilogram and 10 kilograms depending on the task. Larger stones for rough shaping, smaller stones for fine work. No handle, no haft, just a fist-sized rock you held in your hand and struck the workpiece with. He began with a block of andesite he found at Rumiqolqa. He observed first a technical detail that would become central. When he struck the andesite at right angles to the surface, very little happened. The rock barely chipped. When he struck it at an angle of 15 to 25 degrees, it flaked beautifully. The angle mattered enormously. The hammerstone had to come down on the workpiece at a glancing strike, almost a deflection, to remove material. Protzen also found that rotating the hammerstone slightly at the moment of impact increased the amount of material removed per blow. There was a technique, and the technique was specific. With this technique, Protzen began shaping a block to fit a bedding joint. That is, to fit precisely against an already finished surface on another stone. He used the smaller stone as a kind of template. He outlined the contact area, marked it visually, and began removing material from the larger block to match. He pounded with the hammerstone. He stopped. He set the smaller block on top to check the fit. He saw the contact points, high spots, and pounded those down. He reset. He checked. He pounded. He reset. The whole process, Protzen recorded, took 90 minutes. From 2 unconnected andesite blocks at the start to 2 andesite blocks, fitted as tightly as anything in a Sacsayhuaman wall at the end. 90 minutes. Hammerstones only. No iron, no copper, no chemicals. No special knowledge beyond the angle of strike and the protocol of test. Mark, pound, retest. The mystery, in a single experimental afternoon, was solved. There is one detail in Protzen's account that deserves attention, because it changes how you should think about the work. He noted that the hammerstones themselves wore down. A diorite hammerstone, used continuously for shaping andesite, would lose mass at a measurable rate. Small flakes coming off the working face with every few dozen strikes. Over the course of a single day's masonry, a fist-sized hammerstone could lose a quarter of its mass, which means the masons did not just have stones. They had a supply chain of stones. Hammerstone production was its own industry, with its own quarries, its own selection process, its own logistics. Diorite outcrops near Cusco have been identified as hammerstone sources, with archaeological evidence of organized collection. The image of an Inca craftsman casually picking up any rock to do the work is wrong. He picked up a specifically selected, specifically shaped, specifically sized tool, drawn from a state-supplied inventory. And when it wore down, he replaced it from another state-supplied inventory. The whole apparatus of Inca masonry was scaffolded by smaller industries that we rarely see in the popular accounts. There is a video of Protzen's later replications. The work looks unspectacular. A man in a sun hat hits a rock with another rock, sets a second rock on top, looks at it, hits it some more. This is what built Sacsayhuaman. Multiplied by tens of thousands of joints and hundreds of thousands of work hours is what built the Inca Empire's stonework. Not a lost technology, not a softening plant, not aliens. 2 stones, a precise angle of strike, and the patience to test the fit 20 or 30 times until it was right. The technique was mundane. What was extraordinary was the institutional commitment to doing it at scale. For 100 years, we will come back to that institutional commitment because it is the real story. But first, we have to look at where the stones came from, because the work in the wall is only the last step. Before the masons could shape a block, somebody had to pry it out of a mountain. 2 main quarries supplied the Imperial Inca. Rumiqolqa, 35 kilometers southeast of Cusco. Kachiqhata, 4 kilometers southwest of Ollantaytambo. The 2 are different stones, sourced for different reasons, and the difference tells you something about how Inca architects thought. Rumiqolqa is an andesite quarry. Andesite is a volcanic rock, fine-grained, dense, hard, but with a particular property the Inca exploited. It is flow-banded. It cooled in layers, and along those layers, it splits cleanly. The high quarry produces andesite that comes out in thin, even slabs, almost as if the mountain were pre-sliced. The Inca used this for coursed masonry, the rectangular block style, because the natural slab geometry of the rock was exactly what coursed walls needed. Less waste, less primary shaping, more finishing work. Kachiqhata is a granite quarry, specifically a red granite, darker, denser, harder than the Rumiqolqa andesite, and crucially, not flow-banded. The granite at Kachiqhata comes out of 2 large rockfalls below a granite outcrop called neighbours, between 700 and 900 meters above the valley floor. The blocks are irregular, multi-angular, and they had to be shaped from raw forms rather than peeled off in slabs. The Inca used Kachiqhata granite for the most important religious structures at Ollantaytambo, the Sun Temple, the platform of the Wall of the Six Monoliths, the most prestigious work in the complex. So the choice of quarry was not random, it was programmatic. Coursed wall, easy mass production, secular or administrative use. Andesite from Rumiqolqa, polygonal wall, prestige work, ceremonial use. Granite from Kachiqhata, or sometimes the diorite outcrops near Sacsayhuaman. The empire understood its rocks. It understood which rock did what work. It understood that picking the right stone for the job was half the engineering problem. At the quarries themselves, you can still see the working method. Bedrock outcrops are dotted with rectangular extraction scars where slabs were levered out. Around them, dust piles, hammerstone fragments, abandoned half-shaped blocks. The production litter of a workforce that had been there for generations. Protzen and other researchers have found at Kachiqhata blocks that were rough-shaped on site and then transported to Ollantaytambo for finishing. The rough shaping cut down the weight before the long haul. The finishing happened at the building site, where the wall geometry could be checked directly. The geology under Cusco itself is also worth a moment. The Cusco Basin sits on a complex foundation of older sedimentary rocks intruded by volcanic flows, and the immediate area has multiple usable building stones within a few hours' walk of the imperial capital. Limestone outcrops to the northeast, the source of much of the Sacsayhuaman stone, including the largest blocks on the lower terrace. Diorite intrusions to the north and east, the source of hammerstones and of certain dark gray wallstones. Andesite from Rumiqolqa, an hour's mule ride south. Granite and red porphyry, available farther afield. In the Sacred Valley, the Inca did not have to invent a stone supply network from nothing. The geology had given them the inventory. What they invented was the discipline to match each stone to its proper use, and the institutional capacity to extract, dress, and transport the right rock for the right wall every time, across 2,000 kilometers of mountain country for over 100 years. The genius is not in the rocks. The genius is in the system that handled them. There is one piece of evidence at Rumiqolqa that is particularly striking. Some Rumiqolqa andesite has been traced by petrographic analysis to Inca sites 1,000 miles north, to Saraguro in modern Ecuador. 1,000 miles, through mountain passes, across rivers, up and down passes that get above 4,000 meters. The Inca were transporting building stone, not just locally, but along the entire imperial spine. This was a centralized supply chain for ceremonial-grade andesite. The empire did not just have quarries. It had a quarrying industry, with logistics that reached across 2 countries. Which brings us to the next question. How did they move the stones? The answer is, in detail, deeply unromantic. They moved the stones by dragging them. Across rolling logs, across packed earth ramps, across river fords, sometimes lubricated with wet clay to reduce friction, with ropes of braided fiber, pulled by teams of men, sometimes hundreds of men, sometimes thousands. Slowly, over days or weeks per stone, depending on the size and the route. The eyewitness evidence comes from the same Spanish chroniclers who described the masonry. Cieza de León, writing in the late 1540s, described Inca crews moving large stones using log rollers and rope. and noted that the work was organized through the empire's labor tax system, the mita. The mita, in the Inca state, was an obligation. Every adult man owed the state a certain number of days of labor per year, and that labor was directed toward whatever the state needed: agriculture, road maintenance, military service, or major construction projects. For the largest stones, the mita could mobilize crews of thousands. Sometimes the routes were short. The diorite outcrops near Sacsayhuaman were essentially on site. The stones had to be moved hundreds of meters at most. Sometimes the routes were brutal. The granite blocks at Kachiqhata, for example, had to be dragged down the steep slope from the quarry, then lowered down a vertical canyon wall, then transported across the Urubamba River, then hauled up a slope to the Ollantaytambo site. Each step was a separate logistical problem. The slope descent used controlled lowering with ropes anchored to bedrock. The river crossing, based on archaeological evidence of stone-built ramps and channels, appears to have used a temporary diversion of the river to ford with the blocks on log rollers. The final uphill haul used a long earthen ramp, fragments of which still exist today. The numbers matter. The largest blocks at Sacsayhuaman have been estimated at 125 tons. A few estimates place the heaviest at 200 tons. To move a 100-ton block by manpower and log rollers on a graded surface requires a sustained pull of something like 5,000 to 10,000 kilograms of force. That is a coordinated effort by perhaps 400 to 800 men, with rotation, with rest crews, with signal callers to coordinate the tug. The rough estimate from labor economic studies of Inca construction is that Sacsayhuaman alone required, over its construction period, roughly 20,000 workers operating in shifts for somewhere between 50 and 80 years. That is roughly the labor budget of a major Egyptian pyramid, applied to a single fortified hill on the outskirts of the imperial capital. There is also the question of how the Inca got large blocks up onto walls that were already several meters tall. The standard reconstruction, supported by colonial-era illustrations and by archaeological evidence of ramp foundations, is that earthen ramps were built up against the wall as it grew. The ramp grew with the wall. As each course was added, the ramp was extended both in length and in height, providing a graded surface for blocks to be hauled up to the working level. When the wall was complete, the ramp was disassembled and the earth was carted away. This means that during construction, the building site was not the elegant geometric structure we see in tourist photographs today. It was a chaotic combination of partially built wall, mountain of compacted earth, log rollers, work crews, supply caches, and on-site dressing yards, where stones got their final shape before being lifted into place. Imagine a single Sacsayhuaman wall under construction, and you have to imagine the ramp behind it, dwarfing the wall by several factors of magnitude. Once the ramp was gone and the rubble was cleared, what remained was the masonry alone. And the wall, in retrospect, looked as if it had appeared in place by some other means. It had been built behind a landscape of dirt that has long since been swept away. There are also unfinished blocks scattered along the transport routes. At Ollantaytambo, several enormous granite blocks lie on the slope between the river and the site, never installed. The empire collapsed before they reached their destination. They are called, in the local tradition, the piedras cansadas, the tired stones, because the local belief was that the stones became too tired to continue. and stopped where they sit. They are still there. You can walk past them today on the path up to the Sun Temple. They are the most direct physical evidence we have of what Inca stone transport looked like. Frozen mid-move, at the moment the empire ended. Now we have a stone at the building site. We have a quarry. We have a transport system. We have a hammerstone in the mason's hand. We need to bring the block from rough form to wall fit. This is where Protzen's work becomes most useful, because he replicated the entire protocol, and we know now what the masons actually did. The protocol, broken down, is a sequence of test and adjust operations. Imagine you have a block of granite, roughly cubic, perhaps 2 meters on a side, weighing 5 tons. It has been brought from the quarry. Its surfaces are rough. They were quickly dressed at the quarry to take some weight off, but they are far from finished. You need to fit this block into a wall against the upper surface of the block already in place below it. The two surfaces, the bottom of your block and the top of the lower block, need to mate so closely that no light, no paper, no razor blade will pass between them when the block settles into place. You do not have measuring instruments in the European sense. You do not have squares, calipers, spirit levels, or chalk lines. You have the lower block, which is already in the wall and has its top surface dressed. You have the upper block, sitting on a wooden cradle nearby, ready to be fitted. You have hammerstones of various sizes. You have possibly plumbobs of stone or fiber. You have your eyes, your hands, and a workforce. Step 1. Use the lower block as a template. Lift the upper block. Suspend it briefly above the lower block. Lower it down so it rests on the high points of the lower surface. Note where it makes contact. Note where it does not. The contact points will, on andesite, leave small marks of compressed dust. On granite, they leave subtler signs. Slight polish, slight discoloration. Either way, the masons could read them. They mark them, often with a soft pigment. Where the high spots are, you will need to remove material to bring the surface down to a flush match. Step 2. Lift the upper block off the lower block. Set it on its cradle. Bring out the hammerstones. Strike the high spots at the 15 to 25 degree angle Protzen identified. Rotate the hammerstones slightly at impact. Flake off material in small controlled increments. Do not try to take off too much at once. Overcorrection means you have to reshape the lower block too, and that is far more work because the lower block is already in the wall. You err on the side of removing too little. Step 3. Reset the upper block on the lower block. Check again. The high spots should now be lower. Some of them are now too low, meaning material has been removed past the correct level, and there is now a tiny gap rather than a contact point. The other high spots are still too high. You now have a more complex pattern. Mark again, lift again, pound again, reset again. This is the trial and error loop. Protzen documented it in detail. Each iteration takes time. Each iteration brings the surfaces closer to fit. The number of iterations depends on the size of the block, the irregularity of the lower surface, and the precision required. For a coursed block joint, Protzen estimated 5 to 20 iterations. For a polygonal joint, where multiple surfaces have to mate at once, 50 or more. For the most extreme polygonal work, the 12-angled stone, for example, possibly hundreds of iterations across weeks of work. There is one more element, the dust. When andesite or granite is struck repeatedly, Fine dust accumulates between the contact surfaces. The Inca used this. They used the dust as a marker. Compressed dust between the surfaces meant the surfaces had been close enough to mate, with dust as a kind of visible record of where contact occurred. Spreading a thin layer of dust on the lower surface, lowering the upper block, then lifting it again, would leave a clear pattern of contact and non-contact. This is essentially the same principle as engineer's blue, the dye that mechanical engineers use today to mark high spots on mating surfaces. The Inca had figured out the same idea with rock dust 500 years before mechanical engineering was a profession. The end result, after the iteration is complete, is a joint that no razor blade will enter, because there is literally no gap. The two surfaces are not just close. They are matched point for point across their entire contact area. A tightness that, in modern machining, would be called an interference fit, achieved with hammerstones and patience. Now we should ask why the Inca used two different masonry styles. Because they did. Coursed and polygonal. Both produce the no mortar, knife blade fit. Both are present in the imperial heartland, but they are not interchangeable. They appear in different contexts, on different buildings, in different positions within the same wall. The choice was deliberate. Coursed masonry, rectangular blocks in horizontal rows, is the easier style. The blocks are pre-shaped at the quarry to roughly rectangular form, often along the natural cleavage of flow-banded andesite. They arrive at the building site with two of their 6 surfaces already approximately flat. The mason's job is to fine fit 2 more surfaces, the bottom against the previous course, and one side against the previous block in the same course, and the rest can stay rough or be lightly dressed for visible faces. Per block, the labor input is moderate. Quality is consistent. Construction can scale up by adding more crews working independent stretches of wall. Polygonal masonry is harder. There is no pre-shaping at the quarry because the geometry of each polygonal block is specific to its position in the wall. Each block has somewhere between 4 and 12 sides, and every one of those sides has to mate with an adjacent block. The mason cannot know what shape the block needs to be until he sees what its neighbors look like. So the work proceeds slowly, iteratively, block by block. The current block dictates the shape of the next block. Errors accumulate. Crews cannot work in parallel because every block depends on the last. Polygonal masonry is, by every measure, 2 to 5 times more labor-intensive per linear meter of wall than coursed masonry. 2 reasons that we can document, and a third that is debated. The first reason is structural. Polygonal walls, with their interlocking irregular geometry, resist lateral movement better than coursed walls. When the ground shakes, and central Peru is in one of the most seismically active zones on Earth, a coursed wall can slip course over course. A polygonal wall cannot, because there is no continuous shear plane. The blocks lock into one another in 3 dimensions. Earthquakes that cracked coursed Spanish masonry on top of Inca foundations did not crack the polygonal Inca foundations themselves. We will look at the specific events in the next section. The second reason is symbolic. Inca state ideology valued the Sapa Inca, the emperor, as a literal child of the sun, ruling by divine mandate. The empire's most important buildings were religious or administrative declarations of that mandate. Polygonal masonry, because of its labor cost, was a flex. This building is so important that we mobilized hundreds of skilled workers for years to make it impossible to build any cheaper. The visible evidence of the labor was the point. A coursed wall said, "Here is a wall." A polygonal wall said, "Here is a wall, and here are 10,000 worker days you can read in the geometry." The third reason, debated, is aesthetic. Some scholars argue that the Inca simply found polygonal walls more beautiful. There is a clear stylistic continuity from earlier Andean cultures, the Tiwanaku, the Quarry, that used similar interlocking masonry, and the Inca may have inherited a regional aesthetic preference. We do not have Inca-written sources to settle the question, because the Inca did not have writing in the European sense. They had the quipu, knotted cord records, but no narrative texts, so we cannot ask them directly. The aesthetic argument rests on the visual evidence, which is striking but not conclusive. What we can say is that the choice of polygonal versus coursed within a single building was meaningful. At the Coricancha, the Great Sun Temple in Cusco, the lower walls, the foundation, the most sacred level, are polygonal. The upper walls are coursed. As you ascend the building, you ascend from the most labor-intensive, most prestigious geometry to a less prestigious one. The hierarchy is built into the wall. Read from the bottom up, the building tells you what mattered most. The foundation is sacred. The superstructure is utilitarian. 500 years later, we can still read that message in the stones. On the morning of May the 31st, 1650, an earthquake struck the city of Cusco. Modern seismologists, working from contemporary damage records, estimate it at roughly magnitude 8 on the Richter scale. It lasted, by witness accounts, several minutes. A long shake, the kind that gives buildings time to fail in slow motion. By the time the shaking stopped, almost every Spanish colonial structure in the city had been damaged or destroyed. The Cathedral of Cusco was severely damaged. The convents, the mansions of the colonial elite, the new churches, all flattened or unroofed. 19 colonial buildings, including the most prestigious, were ruined. The Inca walls underneath them, in nearly every documented case, did not fail. Not just did not collapse, did not even crack. The polygonal foundations of the Coricancha, for example, were unmoved. The Spanish had built the colonial convent of Santo Domingo on top of the Coricancha foundations. The convent fell. The foundations did not. When the convent was eventually rebuilt in the late 17th century, it was rebuilt on the same Inca base because the base had survived 3 Spanish buildings on top of it and showed no sign of giving way. The same thing happened in 1950, another major earthquake, another round of Spanish colonial destruction. The Inca foundations underneath the destroyed buildings, again, untouched. By that point, the pattern was inescapable. Spanish architecture, with its mortar joints, its rectilinear planning, its imported European logic, was not built for this terrain. Inca architecture, with its mortar-free polygonal masonry, was built for exactly this terrain. The Inca knew their seismology, even if they did not have the word for it. The mechanism, when modern seismic engineers looked at it, turned out to be sophisticated. 3 things working together. First, the polygonal interlock, already discussed, prevents shear failure between blocks. The wall does not slip. Second, the inward batter. Inca walls leaned very slightly inward, typically 2 to 4 degrees from vertical. Under seismic acceleration, this batter helps the wall preload against itself. The lateral push of an earthquake pushes the wall toward its own center of mass rather than tipping it outward. Third, and most subtle, the blocks within the wall are not perfectly rigidly connected. There is just enough elastic give in the contact surfaces. Micro-flexibility from the dust, the slight irregularities, the friction fit rather than rigid weld, that the wall can absorb seismic energy by tiny block-to-block movements, rather than transmitting all of the force to the weakest point. The wall flexes microscopically and then settles. The Spanish cement walls, by contrast, were rigid all the way through. Rigid means brittle. Brittle means catastrophic failure. There is a particular detail that makes this even more striking. Modern seismic codes for unreinforced masonry buildings in the most demanding seismic zones require ground accelerations of roughly 0.3 to 0.4 G. That is, 30 to 40% of the acceleration due to gravity for design loads. Inca polygonal walls have been measured in laboratory shake table experiments and in field observation to withstand accelerations of 0.6 to 0.8 G. They are, in other words, twice as resistant to earthquake damage as the modern code minimum for the same kind of structure. Without engineering calculations, without seismographs, without a written tradition of structural analysis, just by looking at how the ground had behaved in past quakes and adjusting the geometry accordingly, generation by generation, there is one earthquake resistance detail that is worth lingering on because it shows how integrated the Inca approach was. The trapezoidal door and window openings. Every Inca doorway is wider at the bottom than at the top, are themselves a seismic feature. A rectangular opening under a lateral seismic load concentrates stress at its upper corners and tends to crack diagonally outward from there. A trapezoidal opening, by contrast, distributes the lateral stress along an angled lintel surface, reducing the corner concentration. The arch had not yet reached the New World as a structural form. The Inca trapezoid is a workable, low-tech substitute that achieves much of the arch's stress distribution benefit with simpler construction. Look at any Inca doorway in Cusco today. The angle is small, typically 2 to 4 degrees. To a casual viewer, it almost looks rectangular. But the angle is structural, and it appears with remarkable consistency on every important Inca building across 2,000 kilometers of empire. The Inca had figured out, empirically, that the trapezoid handled earthquakes better than the rectangle. They standardized it. The standardization is, in effect, an early form of seismic building code, transmitted not through written documents, but through master-apprentice training across generations of state-employed masons. The Spanish, when they saw all this, did not learn from it. They kept building in the European style. They kept losing buildings to earthquakes. The Inca masonry tradition, for them, was not architectural intelligence. It was peasant work, something to be built on top of, not learned from. By the time anyone in the colonial administration took the question seriously, the labor force that knew the technique was either dead from disease, conscripted into silver mines, or absorbed into churches as Christianized stoneworkers building Catholic structures. The technique survived, barely, in restoration crews working on Inca sites in the modern era. There are still craftsmen in Cusco today who can do what their ancestors did. Not many, a handful. The transmission almost broke. It almost went the way of the softening plant myth. Except that, unlike the myth, the technique was real. And as long as one master could teach one apprentice, the tradition could be kept alive long enough for archaeologists like Protzen to come and write it down. Return to the wall on Hatun Rumiyoc, the single stone with 12 angles, the Piedra de los 12 Ángulos, the 12-angled stone. It is the most photographed object in Cusco. There is a guard who stands beside it during the day, partly to keep tourists from touching it, partly to point out the angles to visitors who cannot count them on their own. The stone sits about 2/3 of the way up the wall, roughly at chest height. It is irregular. It has nothing rectangular about it. It is cut so each of its 12 sides mates perfectly with 12 neighboring blocks. How long did it take to make? We can estimate. Protzen's data suggests that a 4-sided polygonal joint requires perhaps 50 iterations of test-pound-retest. 12 sides on a single stone are more than 3 times that work, and not 3 times, because each angle has to be coherent with the others. So each iteration is more complex. A reasonable estimate is somewhere between 2,000 and 6,000 person-hours of skilled labor, spread across weeks, possibly months, for a single stone, in a single wall, in a city that contains hundreds of similar walls. It is also worth saying out loud how long that work would have lasted in continuous time. 2,000 person-hours at a sustainable working pace is something like 100 days for a single mason. 15 weeks of dawn to dusk shaping. 6,000 hours is closer to 3 years. A single stone, in the most extreme polygonal cases, could occupy a master mason and his junior assistants for an entire growing season, possibly 2. And that mason was not building the wall alone. He was one of dozens working in parallel on the same wall, each of them tied to a specific stone whose neighbors were being shaped by his colleagues. The whole apparatus had to be coordinated. Stones could not be installed until their neighbors were ready. A single delay propagated through the schedule. The whole building site was, in effect, a long-term coordination problem in human time, played out across crews of hundreds of skilled workers and thousands of unskilled support labor. Why bother? This is the question the engineering history rarely asks. You could build a wall that survives earthquakes with much simpler polygonal work. You could build a wall that withstands invasion with a basic coursed style. The 12 angles do not add structural value beyond what 8 or 6 angles would already provide. The 12 angles are not, in any technical sense, necessary. They are excess. They are spectacle. They are an empire showing off. This is the insight that is difficult to appreciate from a tourist photograph. The Inca state poured a category of effort into these walls that has almost no parallel in world architecture. The Egyptian pyramids are larger in mass and more famous, but their geometry is simple. They are stacks of roughly rectangular blocks. The Roman aqueducts are longer and more functional, but their stonework is coursed, mortared, and aesthetically utilitarian. The Inca-fitted polygonal masonry occupies a strange peak. Not the largest, not the most useful, but the most labor-intensive per square meter of any pre-modern construction style we know of. What is that excess for? The standard answer is propaganda. The Inca state, which lacked writing, communicated its power through stone. A peasant from a recently conquered province, walking through Cusco for the first time on a tribute mission, saw walls that he knew, instinctively, his own village could not have built. The labor cost was visible in the geometry. The empire's command of human time was on display. The walls were a written language whose letters were the angles, and the message, in 12 angles on a single stone, was, "We can do this. We can mobilize labor at this scale. Do not test us. The same logic appears in some of the stones at Sacsayhuaman, where individual blocks weigh over 100 tons and have been worked into shapes that interlock with 7, 8, 10 neighbors. Sacsayhuaman was a fortress, yes, but it was also a stage. It was where the imperial elite gathered for state ceremonies. It overlooked the capital. The emperor wanted his subjects to look up and see what could not be made by anyone but him. The walls were both physical defense and symbolic infrastructure. Once you read the walls this way, the labor cost stops being a puzzle. It is the entire point. The empire was not trying to minimize effort. It was trying to maximize visible effort. Visible effort, in a state where there was no writing and no currency, was the only way to communicate fiscal capacity. The 12-angled stone is, in the deepest sense, in ancient Inca tax form. It says, in stone, the Inca state could afford this. By extension, the Inca state could afford anything. So why has nobody done this since? Why are there no modern Inca-style walls? The technique is not a secret. Protzen wrote it up in detail. Other archaeologists have replicated his work. There are restoration crews in Peru today who can produce passable polygonal masonry on demand. The hammerstones are cheap. The andesite is still there. The procedure is documented. We could, in principle, build a Sacsayhuaman today. We do not. And the reasons are all about labor economics. To build a single 12-angled stone takes something on the order of 3,000 person-hours. At a modern American wage of, say, $30 an hour for skilled stonework, that is $90,000 for a single block. To build a Sacsayhuaman scale wall today would require, conservatively, 50,000 stones of comparable complexity, which works out to $4.5 billion of pure labor cost. That is more than the construction budget of any modern public building in the world. The Burj Khalifa, the world's tallest building, was built for $1.5 billion. A Sacsayhuaman today would cost 3 Burj Khalifas and produce, at the end, a single fortified hill. This is the labor economics nobody talks about when they ask how the Inca did it. The Inca did not pay wages in our sense. They had the mita, compulsory labor tax. A worker drafted into Sacsayhuaman construction was, in modern terms, doing prison labor, except that the prison was the empire, and the sentence was a few months a year for life. The same labor, paid at a market wage, would never have been deployed on this work. Nobody would have spent the money. The walls exist because the Inca state had a labor cost structure incompatible with any modern economy. There is a parallel here to the Egyptian pyramids. There is also a parallel to the Gothic cathedrals. Every pre-modern mega-project relied on labor input that today would be either uneconomic or illegal. The pyramids used corvée labor from peasants in the agricultural off-season. The cathedrals used a mix of guild stonemasons, paid relatively well, and lower-skilled labor drawn from religious obligation. The Inca used the mita. The economics of the modern world simply do not reduce these structures. Not because we have lost the knowledge, not because we have lost the will, because we have, thankfully, lost the political economic system that compels free labor at this scale. This is the harder answer to, why don't we build like this anymore? The honest answer is, because the kind of state that did this no longer exists in most of the world, and on the rare occasions when something approximate exists. Slave-built monuments under 20th century totalitarian regimes, state-financed prestige construction in some Gulf states today. The results are typically smaller, faster, and built with industrial machinery rather than hand labor. We have machines. The Inca had hands. The aesthetic of hand-labored precision over hundreds of years is something only a hand-labor empire produces. Once the labor cost structure changes, the aesthetic dies with it. There is one further point worth making here, because it sharpens the labor economics argument. When labor is cheap relative to materials and time, you build for permanence, because permanence is the only way to amortize the labor cost. When labor is expensive relative to materials and time, you build for replacement. Fast, cheap, repaired or torn down on a 30-year cycle. The Inca walls represent the extreme of the first regime. Modern American suburban construction represents the extreme of the second. The cost per square foot comparison, naively, makes the modern style look efficient. The cost per century comparison reverses it. A square meter of Inca polygonal wall, amortized over 500 years of standing, is essentially free. A square meter of modern wood frame stucco wall, replaced every 50 years, has been built 10 times over the same period, and costs, on a present value basis, several times more than the Inca wall ever did. The Inca built once and never had to build again. We build constantly and never quite finish. Which approach is rational depends entirely on how long you expect your civilization to be there. The Inca, when they built, expected forever. We do not. There are small modern attempts. There is a stonemason in Cusco named Eric Cardenas, who has been working with traditional Inca techniques for decades, partly for restoration, partly for educational demonstrations. There are projects, mostly funded by tourism boards or by UNESCO grants, that produce small sections of polygonal wall as training pieces or as repairs. None of these projects is at imperial scale. None of them attempts a full Sacsayhuaman, because nobody has the labor budget for it. So we are left with the existing walls. They are, in a sense, fossils, perfectly preserved, fully documented, but representative of a labor economy that does not return. We can study them. We can replicate small pieces of them. We cannot build them again. The technique is ours. The civilization is not. So what do you take from this? 500 years after the empire fell, what is the lesson encoded in 12 angles on a single stone in a narrow Cusco street? The first thing, and the easiest, is the technique itself. You do not need lasers to do precision stonework. You do not need iron. You need patience, an understanding of how rock flakes when struck at the right angle, and the willingness to test, mark, pound, and retest. The Inca did this for centuries. Modern stoneworkers, Eric Cardenas in Cusco, restoration teams at Sacsayhuaman, and a handful of independent practitioners around the world still do it. If you are inclined toward stonework, this is a craft you can learn. The instructions are in Protzen's book. The materials are everywhere. The barrier is only labor and time. The second thing is harder and more useful. The Inca walls are an argument about what civilizations spend their labor on. We, meaning industrial modernity, spend our labor on speed, scale, and disposability. We build 100 buildings in the time the Inca built one wall, and most of our buildings will not last 50 years. The Inca built fewer buildings. The buildings they built will outlast every cathedral, every condominium, every civic center we have erected since. The labor quality trade-off the Inca made and the labor volume trade-off we have made are opposite poles. Neither is wholly correct, but the Inca pole is worth understanding because it shows what the other extreme looks like and what it costs. and what it produces. The third thing is the lesson about evidence. The Inca walls, for 400 years, were treated as a mystery. Lost technology, aliens, softened stone. Generations of European writers, generations of modern conspiracy theorists, generations of half-informed tourist guides, all spitting theories about a problem that one professor with a stone hammer solved in 90 minutes in the early 1980s. The mystery existed because nobody had bothered to test the obvious explanation. When Protzen tested it, the explanation worked. The mystery dissolved. This pattern recurs. There are still topics in popular history: Egyptian pyramid construction, Roman concrete, Greek fire, ancient navigation, dozens more, where the mainstream popular treatment is, "We don't know," or "Scientists are baffled." And the academic literature has had a perfectly good answer for decades. The gap is not knowledge. The gap is publicity. Mystery sells better than explanation. The Codex tries, where it can, to close that gap, to say, yes, we know how. Here's who figured it out. Here's what they did. What you can do in your own life is be a little harder on the mystery framings when you encounter them. When somebody tells you a piece of ancient construction is unexplainable, ask who has tried. Ask what they found. Ask whether the mystery is in the artifact or in the marketing. Most of the time, you will find the mystery is in the marketing. The Codex closes on this entry with 12 angles in a single stone, in a narrow street in Cusco, and a hammerstone in the hand of a Swiss professor who walked into a quarry one afternoon and made the impossible take 90 minutes. 2 empires made these walls: the Inca, who built them, and the Spanish, who tried to bury them and failed. The walls are still there. They will outlast everything we are building today. And the next time you see one, in a photograph or in person, you will know what made it. Not magic, not lost technology. A man with a rock and the patience to test his work 20,000 times until it was right. That is the entire mystery. And it is, in the end, the only kind of mystery worth having.